Welcome to the 21st lecture video for Physics 4C. We continue our fully quantum mechanical treatment of physical systems from last lecture, setting up the stage for the next week when we will use the tools we have introduced to predict experimental outcomes. First, let's recap a little bit of our intro to wave mechanics from last lecture to make sure our understanding of wave function, operators, and measurements in quantum mechanics is solid. Then, we will address what happens in a measurement process. If an electron is a wave, does that mean when we measure its position, we will measure a spread out thing? The answer is no, but it's more interesting than just a no. And then we address what is sometimes known as the Heisenberg uncertainty principle, or just uncertainty principle, relating the precision in position measurements to the theoretical limit to the precision of simultaneous momentum measurement. These ideas can be a bit too abstract, so we have a video with a PhET simulation demonstration, which will hopefully give you some intuitive feel for all these. And finally, the last lecture segment is setting us up for the next week, when we will calculate expectation values. That is, predictions of experimental outcomes using the wave function. And in order to use the wave function in this way, we need to be able to normalize it, having given the absolute value squared of the wave function its correct meaning as probability density. Next week, we continue with our coverage of wave mechanics, covering much of section 7.1 of OpenStax University Physics Volume 3, and looking at the quantum harmonic oscillator solutions. So this would be recap of intro, everything's introduction to wave mechanics. So this is the first view of a fully quantum mechanical approach. And I would like to start out with a bit of a mathematical statement, which is that that there exists a wave function that's a function of position and time, and this position is potentially three-dimensional position. And what's special about this wave function is that it contains everything there is to know about the setup. So there exists a wave function that contains all information about the state. Let me not define what state is. I had a upper division quantum mechanics professor who actually started out with something like that. He had postulates of quantum mechanics, he called it. I'm not going to go that far because he was a particle physics theorist. I think he felt more comfortable doing that. I'm not going to call these postulates, but we're going to use this as a starting point. It's an important statement to make as a starting point, because when we do wave mechanics, the rest of what we do is we are pulling information out of this wave function. So we need a way to measure things. Well, we need a bunch of things. A way to measure physical observables. And I'm going to make a suggestion that what I'm calling physical observables, measurable quantities, at this point in the game, we really have only three basic observables we need. Once we can measure those three, all the other quantities we can kind of construct out of them. And those physical observables are, we need to be able to measure position, we need to be able to measure momentum of the state, and we need to able to measure energy of the state. And how to measure these observables? Physical observables are measured using operators. And let me just give them a symbol, or give them symbols. So the position operator would be that symbol. And I'm going to put a head on it to distinguish it from the measurement position. And for momentum, same symbol. I'm gonna put a head on it to distinguish it from the measured momentum. And the energy, I'm gonna put a head on it. And the way measurements are made, measurement goes like, so this is where it's important that we said the wave function contains all the information. So we are trying to pull this information out of the wave function. And for simplicity's sake, I'll say this wave function has a definite value of position, definite value of momentum, definite value of energy. And for this mythical wave function that has those definite values, the way it would work is, well, we take this wave function, we operate on it with the operator, and if it has the definite value of position, then we'll get the same wave function back. This thing that's a function of position and time will have the same function back, and we'll have some numerical value here that wasn't there before. And this is the measurement. This is the measured value of position. And the same goes for momentum. Acting on the wave function with the operator will, if the wave function has the definite value of momentum, we'll get the same wave function back multiplied with some number. And this number will be the measured value. Same thing with the energy. We'll have the, if this wave function has definite value of energy, we'll get the same wave function back. And there will be some number that's in front of it. That will be our measurement of energy. It's a really, so I think if you've taken linear algebra and know something about eigenvalues, then this would make more sense. Until that point, you'll just have to take this as a given. I think that's why my quantum mechanics professor called it postulate, because you take these as given. You don't reason it. That's just a true statement. You accept them as being true. So with this foundation laid, really the key thing that you need to know is the representation of these operators. So the position operator, and this is, by the way, in the this is in a position space, which is, I'm going a little bit more abstract than, we are only going to work in position space. We're not going to work in momentum space. So in position space, the position operator, it's actually just x. You multiply by x, that's acting on a function with the position operator. Momentum operator looks more interesting. It looks like, so it involves a derivative with respect to position. And in fact, this position, it's related to the component of the momentum that you are looking at. So x component is the derivative with respect to x. As an example, y component would be related to the derivative with respect to y, and so on. And this doesn't have the right units for momentum. So for the right units, you need h bar over imaginary number. H bar over imaginary number. So this is the operator. I think here you can more easily see that, yeah, that is an operator, as in this derivative operation. It's hungry for a function to act on. It's only after you act on a function, you get something mathematically tractable that you can get a handle on and work with. And finally, the energy operator, which we don't really use as much, but it does get brought up, especially when you go from the time-dependent Schrodinger equation to time-independent Schrodinger equation. The energy operator, it's related to the derivative with respect to time. So you take the wave function, which is a function of position and time, and take the partial derivative with respect to time. And if it's an energy eigenstate, you should get the same wave function back. And I still need a coefficient here, h bar times I. I think that gives me energy. Yeah. So these are the operators. And once you have these, then, for example, Schrodinger equation. What Schrodinger equation says is this. Schrodinger equation says, well, momentum squared over 2m, that's kinetic energy, plus the potential energy, which by definition of potential energy is function of position alone. So this will give me some kind of an operator that can act on a wave function. Hey, kinetic energy plus potential energy, that looks like a total energy. So we say that's equal to, well, energy of the state, which we'll measure out of the wave function. So this is the Schrodinger equation. And I will leave it up to you to plug in these expressions for momentum, position, and energy operators, and see that it does give you the second order partial differential equation that's listed in your textbook as a Schrodinger equation. So that's the recap of intro to wave mechanics, kind of the fundamental assumptions underlying wave mechanics. And because at the end of this, you have partial differential equations. It's mathematically very challenging. And as I say in lecture, we'll only look at for complete solutions, we'll only look at the simplest possible cases. Except for the simplest possible cases, it's really out of our depth to solve this partial differential equation. So we won't go there. Let me try to set up the stage as well as I can. And the two main things I want to really address in the lecture now is the two very quantum mechanical ideas that's not easy to understand from the classical mindset. One is the idea of measurement, which can actually become super mystical if you are bent that way. And I want to avoid that as much as possible. Like when you talk about New Age people, like I want to stay away from all of that as much as possible. So last Tuesday, I just talked a little bit about measuring position of a particle in an infinite square well, and all of that can be a little bit abstract. So I want to give you a more concrete physical scenario. I don't have a real demo, but I can show you a simulation so that you can see in a real experiment what it would look like. And the other thing that I really need to go over is the uncertainty principle. There is a natural way to understand it in a way that it kind of makes sense, and that's actually a good chunk of what your lab addresses. But I want to set up some kind of stage for that. So on measurement, so this is what we talked about last time, so that we are not just coming from vacuum. If we have infinite square well, that is, if you have a particle of mass m that's placed inside some potential wall, never mind how you're building it. If you're actually doing the experiment, you will do it with the electric field. But the idea is that this particle is confined within some limited region, because if it goes too far one way, the potential goes to infinity as it's trying to go beyond this. So no matter what, it won't have enough energy to go beyond this. And the same thing happens at the other end. And this is the situation that we call infinite square well. And we looked at the wave functions, which can fit in here. That's consistent with the quantum mechanical assumptions that we've been introducing since 2 weeks ago. So the one example of wave function that we looked at was something that looked like this. Let me draw some pictures that you're going to start seeing a lot. So people like to combine several pieces of information into one drawing like this. One is, so you saw the different energy levels that were allowed, right? So the allowed energy levels, let me see if I can remember. This is how I will best remember it. It's kinetic energy. Whatever energy you have, it's all kinetic energy. And what's nice here is that momentum had the particular allowed values in it, because momentum was related to wavelength by this relationship. And if we are trying to fit in standing waves here, only certain wavelengths fit. So we do all this as memory aid. I think this is what it ended up being. The allowed energies were
n squared h squared over 8ml squared, where L would be the width of the well. That's what you remember? Yes. So this can be represented in this diagram this way. I can draw the energy levels. So this should be the, let's say, energy level for the first allowed level. That's the ground state energy. Then looking at this expression, as you change n, the only thing that, well, only n changes. Everything else is constant. So the next one is at 4 times the amount of energy of this. So this is 1 unit. So the next one will be 4 units from the bottom or 3 units above this. So 1, 2, 3. So this is the next energy level. And I'm not sure if I can draw the next one. Next one is 5 units above this. So 1, 2, 3, 4, 5. Okay, I think that's the most I can draw on this limited scale. So this is one way of kind of representing the allowed energy levels in this one diagram. I'm kind of making use of the fact that I'm already using the vertical axis to represent the potential energy. So if I'm drawing total energy, it'll be same on the same energy scale vertically. And now that you have this as a baseline, the way people like to draw these pictures is use this as the 0x or the x-axis. So this is the sort of wave function equals 0 line for the 3 allowed states that we are going to draw. The wave function that corresponds to this energy level, one that corresponds to this energy level, one that corresponds to this energy level. And we looked at this last time. Those wave functions look like, so this is the longest wavelength that fits. This is the next longest wavelength that fits. And this is the next longest wavelength that fits, right? And these are all representing the wave function psi1, psi2, psi3. And I'm drawing a snapshot. Over time, this will oscillate up and down like standing wave. Okay? And what we looked at last time was, so let's say this represents a particle of mass m. This wave function is somehow representing a particle of mass m. And like an electron, and it's a particle so small that it doesn't really have a known size, or it's much, much small compared to this length L. And what I claimed last time is if you were to measure the position of this particle, let's say you prepare in this state, and you measure its position, you are not going to actually see it spread out all over. You are going to measure it at a particular location, the way it ought to be. So like one time you might measure it here. This is one of the most likely places to be. So, that's one of the most likely places you'll find it maybe. But by almost a random chance, sometimes it'll be here, sometimes it'll be here. And if I draw something that looks like a histogram, so this is what I drew towards the end of the class last time, you'll get this kind of distribution for particle detection. So there are some patterns you can see. As in, when you look at the distribution of, so you have to imagine doing 100 different experiments to build up statistics like this. And when you do that, you see a pattern that particle is most likely found at some location, but not only at that location. And then particle is not likely to be found at all at certain locations. They would be like nodes of the standing wave. And this is represented by the psi to absolute squared. And we talked about last time what that absolute squared means. Okay? So now all of this is very abstract. It's kind of easy to get lost in the mathematical description, hear it, and just not have any sense of what any of this meant. So that's why I want to show you this simulation, because this simulation will connect to something that you have already seen. It's this is not the first time you're dealing with the waves. You have dealt with it in 4A. You dealt with it when we were doing optics. And that's kind of why we do optics in this semester, because that gives you a kind of a place where you can ground your intuition on. Optics, they are, wave optics are more interesting than geometric optics, but they are not, they are not so unintuitively difficult like quantum mechanics can be. So let me bring up, see if I can remember which simulation it is I wanted to use. I think it would say wave interference. Maybe this is what I'm looking for. It says quantum wave interference, so that must be it, right? Let me try it. So what I want to start out with is the description of Young's. So I've been talking about the infinite square because that's the easiest thing to solve for, but it's also very artificial, very abstract. So the actual realistic experiment dealing with the quantum mechanics would be something like Young's double slit experiment, something that would illustrate wave properties of whatever it is you're looking at. So we could say, do I have lasers? Oh, 2 lasers. I don't know what that is. Let me just be here. All right, turn on the laser. Maybe I should turn off. Oh, okay, I didn't turn it off. All right, this might be too bright. Let me just put it. Let me reset everything. Reset. All right, let's see. So this is kind of illustrating intensity of the dot. So, imagine this. This is green laser. Imagine I'm shining it here. So that's a like zoomed up version of this dot, right? And so you want to show the wave property of this light that's hitting the wall or screen. So in order to show wave property, you put in a double slit. Then I probably need to make it a little bit dimmer. So this is what you would see when you do the Young's double slit interference experiment, and this was the basis on which we said light is a wave, right? Yeah. Now, so I want to show you what it means. One of the sort of consequence of us acknowledging that light is also a particle. So what you are seeing here is a high intensity situation. You did this estimate on the photoelectric effect lab, I think. How many light photons are there in 1 watt of light bulb emitting, like 10 to 20 or something, right? So when you have that many particles, it's easy for the particle nature to get just buried in that large number of particles. Like when you see a cup of water, you don't see individual water molecule, but I assume most of us here believe in the existence of water molecules, right? Okay. So what I want to do is I want to show you what it would look like if we reduce the intensity down a lot and fired essentially such a small intensity that reduce the 1 watt intensity down by a factor of 10 to the 20. So that if you detect any light at all, you would be detecting only 1 single photon at a time. So that's what I believe what this is supposed to be for. Let me set up everything the exact same way I have things here. So I think I want the screen to not fade because I'm going to be firing very slowly. Let me put double slit here. Probably the same parameter as the other one. All right. So this is one way of demonstrating the particle nature of photon. When you fire this is, well, you wouldn't see this. When the light hits the screen, this is what you see. You see a single photon. You can imagine there's a very sensitive detector called a photomultiplier. These are so sensitive they can actually detect single individual photons with like 20% efficiency. So you can imagine having an array of those very sensitive light detectors. They are so sensitive that if you shine too much light on it, you will ruin them. So you do this in a dark room very carefully. So you have an array of, let's say, 100 of them, so you can detect where the light falls there, if you detect one at all. So you fire one at a time, and each time, what you're finding is that each time, of the 100 photomultipliers you have only one registering at a given time. And you can also do this with the CCD. What does CCD stand for? CMOS something detector? Everyone here knows what CCD is, right? Light sensor on your digital cameras? Yeah? Yeah. If those are sensitive enough, they can also kind of count one photon at a time, but not as well as photomultiplier. But this is what you would see. As you fire one photon at a time, you would, as you emit such a small amount of light that there can really only be 1 or 2 photons, you see those particles detected at some location. And this is what I mean. It'll kind of seem random, right? It seems random. I don't know if I can, I can do rapid. Because all of this is just the animation. You wouldn't actually see that. So let me just do rapid. So, all right. So you keep firing and you think, so I guess light is particle after all. Light is not wave. But that's not quite right, because when you did this experiment, this wasn't wrong. No one faked this result. At least, well, you guys did the interference and diffraction lab. You didn't fake anything. You saw what you saw, right? So this result is still right. So let's say, you do this and you just keep firing, hoping you will see something different. And as I said, you have to do this maybe 100, 1,000, large number of times that you get some statistically significant number of particles. Then after a while, you begin to build up a pattern. Let's see, can I? Okay, this is a good pattern.
Auto repeat, I think.
Where? Oh, there? Okay, that's a lot better, thank you. All right, let's wait for a bit. Yeah, I wasn't really keen on firing it, clicking it 1,000 times. All right, so maybe some of you see the pattern, maybe you don't yet. I don't want to fire for too long because the pattern could get also washed up a little bit. Okay, I think this is probably good enough. So you can almost imagine a very grainy picture that's taken at very low light conditions, especially if you do it with a film, like a high speed, high ISO film. Okay, let me just stop it here. Stop the auto repeat. So this is some kind of intensity pattern you are now starting to build up. Compare it to this. Do you see similarity? Yeah. Where there was no intensity, somehow, even though each time you are detecting single particle at a time, those particles have zero probability of falling here or here. But each time you detect a particle, you don't see this pattern. You know there's this underlying pattern here because one, you see it when you have a high number of particles. And this is really the thing that'll, if you get too deep into it, will get you philosophically messed up maybe. Even when you fire such a small amount of light that only one gets detected at a time, there is some kind of underlying influence that's never letting the particle fall along this line. So this is what I was trying to describe here, that each time you detect a particle, each time you fire this and you detect a particle there, you detect it as a particle, a single, very narrow location thing. But after you have collected enough of them, you see the pattern that you can attribute to the wave nature somehow, because this dark fringe, you would only see it with the destructive interference. So that's probably where I should leave the whole topic of measurement on, because frankly, it is, I keep telling people this, it is an area of active research, what is really truly meant by quantum measurement. The simulation you are going to run in today's lab, it's from the approved curriculum. So it's teaching you the mainstream interpretation, which is known as Copenhagen interpretation, that posits a wave function collapse. That you have a wave function that looks like this. The moment you measure the position, the postulate is that wave function collapses into a form. So if you detected a particle here, that means your wave function collapsed with the act of measurement, that now your wave function takes this form. That's the interpretation that the simulations you're working with in today's lab is based on. I'm not asking you to accept that blindly. I'm not telling you that's necessarily the correct final answer. I'm telling you that's what I'm required to teach you. That's the mainstream interpretation. Yeah.
So does that kind of mean that right before the photon hits that sensor, that it can be anywhere there, and it's the second you read it, then it?
Yeah, so let me give you this, rephrase that question in a slightly different way. So you are wondering, all right, so you know, let me clear this up, reset. So you know that once the light wave hits the screen, photon was detected here, photon is there. All right, you accept that. So you're asking, where was the photon right before it hit, right? Let me ask you a slightly different question. Which of these two slits did the photon go through? Does that sound like a valid question? Yeah, so I think this ought to be described in your textbook somewhere. So people do this experiment. So when you are doing this, once again, I keep saying that you would not see this pattern. So like, this is just the artist's rendering of what the wave must have been doing. So let's say you are not satisfied with artist's rendering. You want to actually see which of these two slits the photon is going through. So the only way to do that is you put a detector here, and you kind of try to measure, is the photon going through this slit, or is it going through this slit? And once you set up that experiment, once you set up your experiment to detect which of these two slits is your photon going through, or I guess your textbook might describe electron actually, which of these two slits your electron goes through, then the interference pattern gets wiped out. You don't actually see any interference. So you see it, so you will detect the particle going through either this slit or this slit, and the pattern you see is becomes very consistent with the particle interpretation of light. You see no interference pattern, you see no destructive interference, and that's actually related to the next thing I want to talk about, something called uncertainty principle. And that's actually related to the next thing I want to talk about, something called uncertainty principle. And I said that this is going to be a theme in Physics 4C, that we are going to start admitting to some of the idealizations that we held in classical mechanics, that something could move as fast as you want it to move. Turns out it can't. Speed of light is the universal speed limit. And in classical mechanics, maybe we didn't say this explicitly. There was this underlying assumption that you could make any measurement as precisely as possible. With the quantum mechanics, now there's an admission that even in theory, that's not possible. Even in theory, there's a limit to precision. Actually, I felt like, oh, we had this already. We had this discussion. Resolution limit, diffraction limit to the resolution limit, right? And this is kind of an extension of that. So let me describe this uncertainty principle. Let's see, let me give you the actual expression. I don't know if your textbook has this one. Let me give you the correct expression, because oftentimes you get the approximate version. And okay, I will write that too, but let me give you the correct one. So the uncertainty principle, it relates the precision with which measure two different quantities. I spelled it out here so that it's, sometimes people call it Heisenberg uncertainty principle, and like, what does that mean? So what you are measuring are momentum, or P, and position, or X. So the uncertainty that you are looking at is related to the uncertainty or error in measuring the position and momentum of a particle like this. And the approximate version you might have seen is something like this. Let me write it down so that you can at least recognize the form. It says that if you have uncertainty measuring position, and that's going to be associated with the related uncertainty in measuring momentum of the same particle at the same moment in time, then this uncertainty must be greater than equal to roughly Planck's constant. So in case you see this in a textbook, sure, that's close enough, it's not wrong. Let me give you the very precise version. So I put this approximate thing. Well, so in upper division, you will see it's a sort of like, when you do make measurements and you put on error bar, how precise do you need to be on the error bar? Do you want 1 significant figure, 2 significant figure, 5 significant figures? At some point, it's kind of silly, right? You're talking about the error bar, not the measurement. That's why this is still useful, because you're only talking about the limit on your precision, not the actual number you're measuring. But that's why I'm saying this is kind of a more upper division material. When you formulate quantum mechanics rigorously, you build this into your theory so that this is your fundamental limit. It's not a matter of you could design a better experiment. You could design the best experiment possible, and you will always be limited by this. the uncertainty in position times uncertainty in momentum is greater than or equal to. There are some very limited situations where it's actually exactly equal to h bar over 2. So, there's a factor of 4 pi missing here, obviously. So that's the exact relationship. And this is related to, this is related to some mathematical structure that you will see in upper division quantum mechanics. But for now, I guess what I want to do is I want to give you some intuitive sense why this should actually be true. Wait, before we get into it, let me give you the exact definitions of this and this, so that, because if you're trying to be exact here, these better be exactly defined. It's not like you eyeballing what is my uncertainty in X, what is my, there's a very precise statistical definition for delta X and delta P. These need to be standard deviation of X, and it would be the same thing for this. Standard deviation of P. Everyone here knows what standard deviation is? Yeah. So everyone here knows the bell curve, the normal distribution. So normal distribution kind of looks like this. Let me just do it for X. So X position could look like this. Maybe, so this would be the frequency of how often you measure it. It's like a histogram once again. And as you measure the X position of something, sometimes you measure it at X equals 0, sometimes out here. So the histogram plot kind of looks like this. So this would be something that's on average at X equals to 0. And there's a mathematical form for what this looks like. The frequency as a function of X looks like, I'm not going to normalize it because I don't remember the normalization factor. It looks like e to the minus x squared over, I want to say 2 sigma squared. Is that right? How many people here have taken statistics? Does this look about right? Yes, so at x equals 0, it's at 1. And as you go farther away, as x gets larger, it gets smaller and smaller. It's negative exponential. And same thing with as x gets more negative. And this quantity sigma is the quantity parameter we can use to sort of describe the width of this pattern. So this would be what? This would be sigma. And if you took statistics, then what they should have told you is that within 1 sigma, so within this, there should be something like, I don't know, approximately 30% of your population there or something. So if it's within 1 sigma on both sides, it's approximately 60%. You go 2 sigmas out, it's like 90%, right? Yes?
34%.
Maybe, I don't know. I don't have all the numbers memorized, but you get the basic idea. So when we want to give this a precise statement, there is a precise mathematical definition for delta x and delta p. It's that it's the standard deviation of the distribution of the quantity that you are trying to measure. Yeah. So I'll leave it there. In upper division, they do more. There's some algebraic manipulation you can do to. I guess maybe I should give you the definition of standard deviation. So standard deviation of x is defined as this. Let's see. You take each individual value of the thing that you measure. You subtract off the average of that value that you are trying to measure. You square it, and then you average it again. Right?
The square root whole thing?
Oh, yeah. Average it, and then square root the whole thing. So this is the definition of sigma of x. And in upper division quantum mechanics, there are some algebraic manipulation you do to actually make that a little bit simpler. We won't do that. It's not really necessary for us. So that's a statement of uncertainty principle. But the way you hear it, it's like, it's like me telling you Martians have landed in San Francisco. Like, why? Why are there Martians in San Francisco? There's no intuitive reason why this should be true. And it doesn't have to be. There is actually intuitive reason why this has to be true. And all this ties into de Broglie relationship. That's why I told you guys from the beginning that the de Broglie relationship, that anything that has momentum has a wavelength that it can be related to. H over lambda. This is your gateway between classical world momentum and the quantum mechanical world wavelength. So let me try to illustrate, demonstrate a particle, demonstrate something that has as precise a momentum as possible. So that means it has as precise a wavelength as possible, right? And the functions that have precise, well-defined wavelength are the sinusoidal functions, right? Or complex exponential. For my wave function, let me just take a snapshot. So at t equals 0, might look something like some amplitude times e to the I guess let me write out in terms of lambda. So the I 2 pi x over lambda. Right? Let me sketch the real part of this. So on this axis with x. So let's say if I'm doing the real part, it's actually cosine. So at x equals 0, I would be starting from 1 or a. And as I go farther out, it looks like cosine. All right. Can I ever stop? Or does this have to go forever? Yeah, forever. If I ever stop, then that's not my wave function. If I ever stop, then that means, it's x less than some value x max. And it's the same deal on the other side. If I ever stop on the other side, then it's, if I ever stop, then it's for x greater than some x min. But so if I'm somehow putting this restriction on this function, then it's no longer this complex exponential. It's the complex exponential limited to this. And the outside of that range, it'll be 0, 0 for below the minimum and above the maximum. So the function that has a precisely defined wavelength is not this. You cannot limit it to spatial distribution. You have to let it roam freely from negative infinity to positive infinity. So this is what you have. Because of spatial limitations, I stopped, but it's supposed to go on forever. So if someone were to ask you, where is this particle? Where is it? It's everywhere. That's what I was telling you about the plane wave solution last time. Plane wave solution represents a particle that's everywhere. So this is what you have here. In this particular, somewhat absurd picture that you wouldn't really see in real experiment, you have uncertainty in momentum go to 0 because the uncertainty in wavelength was 0. And you have uncertainty in position as a result of the fact that this wave function is all over the entire space. The uncertainty in position also has to go to infinity. So I guess let me ask you this question. Is this consistent with this? Kinda, right? In a kind of vacuous sense, it's infinity times 0. You can make the number whatever you want it to be. Maybe it's greater than h bar over 2. Maybe it's smaller. You wouldn't know. But at least this is giving you that in a very naive picture where you said, oh, I don't need to have any uncertainty in momentum because I can define a function that has precisely one wavelength. Then you are saying, oh, that's not quite right. It does have, if it has a 0 uncertainty in momentum, that leads to arbitrarily large uncertainty in position. So let me give you a more realistic picture. More realistic picture might be something like this. So, all right, let's say I'm going to give up on my dream of having the arbitrarily precise momentum measurement. So I'm going to say, all right, take this function and then multiply it by, oh, I guess I can do it with the different things, but I kind of want to multiply with this, with a normal function, so that, let's say I multiply it with e to the minus x squared over 2 sigma squared. Then what that does is it lets me localize this particle. So let me shift my x equals 0 over so that I can actually draw both sides reasonably well. So this is my x equals 0. And let me just draw the envelope so that I know what I'm fitting where. My envelope, represented by this, might look something like this. So maximum here, something like this. And I'm going to increase my momentum or decrease my wavelength so that I can fit in something that looks kind of wavy. So what my wave function will now look like, that's represented by this, will be something like this. So it's this sinusoidal oscillation multiplied by the normal function envelope. So it would look something like, so starting from here. As it goes here, it'll oscillate, go all the way negative. So there will be a kind of mirror version of this normal thing on the bottom. And this will kind of fit in, oscillate in between these two until it goes to 0. So this is what this new wave function will look like if I insist on making sure that my position uncertainty is an infinite, because if you don't already hate infinity, you should hate infinity. Infinities are nasty. You don't really want to see them in your description of anything. That's why, there's a reason astronomers say visible universe. Because, yeah, visible universe is not infinite, but the actual universe might be infinite. So this is a somewhat nicely behaved wave function, which has limited spatial extent. So if someone asks you, what is the uncertainty in delta x? I can actually tell you what it is. So this is a sigma. This is my sigma. And I can say my uncertainty in delta x, uncertainty in position is sigma. Or that's actually how I defined uncertainty. Yeah? And I might be missing factors of 2 here, by the way. So don't push me too much here. Yeah, so I'll be hand wavy there. So you have a situation set up where the uncertainty in position is reasonably limited. It's not 0, because you can kind of imagine how ugly this will begin to look if you're trying to squeeze this down to 0. So we are not greedy. We are just setting it at some nice finite value. And this would be the question. Can we now say that the uncertainty in momentum, can we still say that uncertainty in momentum is 0? I mean, after all, you have one wavelength here. So this is where, so in your lab, we will address this under something called Fourier analysis. The idea is that this wave packet can be represented as a superposition of a bunch of these. And the way you would build up this wave packet is by, so there is, so if you're trying to say this is your wavelength, then what you're trying to say is this. You're trying to say, all right, I'm starting from here, go to here, and you are trying to say this is your wavelength. And well, so your wave packet does have a component to wave that has that wavelength. But that component, it looks like this. Its magnitude doesn't vary. It has a constant amplitude that, that doesn't change. That'll just oscillate up and down. So in order to build this wave packet, what you need to do is you need to bring in additional other waves that have different wavelength. So, I guess I'm kind of running out of time. So let me just call this. So let me put it this way: under something called Fourier analysis, an aspect of which you will see in one of the simulations that you're doing in the lab. This, meaning this, is a superposition, meaning sum of many different wavelengths. And you will see this more intuitively in the lab. As you are changing the parameters in the simulation, you will see that if you are trying to make the position uncertainty smaller, that makes the uncertainty in the wavelength, or your lab actually deals with the wave number, uncertainty in the wave number greater. That leads to greater uncertainty in the momentum. And so notice how, so far I haven't brought in really anything quantum mechanical. I'm just describing waves, right? So there is a classical wave number position uncertainty. If you have a classical wave and you want to confine it within some region, then there will be an uncertainty in the wavelength or wave number because you have to combine many different wavelengths to get that localization of the wave. The quantum mechanical piece is this, that when you have that uncertainty in the wavelength, that translates to the uncertainty in momentum. Yeah. So if this makes sense, then this uncertainty principle is not really new. If you're good enough in math, then this is something you could drive mathematically from a wave number position uncertainty principle in classical waves. Okay. So I have a few minutes remaining. Let me give you a more concrete example. I guess I'm using the word concrete in the sense that you can actually look at the numbers. I want to use this as a concrete example. So, infinite square well, it's, it's a made-up example. You don't really have infinite square wells in real life. But it gives us very nice solutions. For one, we already know what these wave functions are, the time-independent solutions. We looked at this last time. These are, a sine of pi x over lambda L, a sine of 2 pi x over L, and this is a sine of 3 pi x over L, and so on. Now, one could say this. What would you say is the maximum position uncertainty for particles in this square well? What is, just intuitively speaking, knowing what you know about this setup, what would you say is the maximum possible uncertainty in position? L, right? Yeah, particle is confined within this range. So this would, the actual uncertainty, the way we define it here, could be smaller than L, but it's at least smaller than L. It's never going to be bigger than L, right? Because you confine the particle here.
Wouldn't it be the standard deviation of L?
Yeah, but this is what I'm saying. If I actually measure the, maximum. So if I measure the actual uncertainty, the most it can be is L. Good. All right. Now this is something that I'm hoping causes a little bit of a puzzlement. When you look at these solutions, look at this one for example. Superficially, does it look like superficially that your wavelength is exactly L? Which means, delta lambda equal to 0, which would mean that your momentum is exactly h over lambda, so h over L, and which would also mean that your uncertainty in momentum is exactly 0. That would be inconsistent with this, right? Because then, if this uncertainty principle is correct, uncertainty principle is claiming that delta x times delta p is greater than approximately h, And here, I seem to have an example where 0 times a finite number is 0. So what am I missing?
Energy level.
Energy doesn't enter here. I've picked this exact state. So it has some finite energy level, but I don't have to, and energy doesn't have to enter any calculation anywhere. I'm missing something here. What am I missing? What would you say the average velocity of this particle is? Note carefully how I said the velocity, not speed.
0.
It's a standing wave. Is it going anywhere? Not on average. So the average velocity would be 0. So that means average momentum must be 0. Yeah, that's not consistent with this. So what am I skipping out here? I'm kind of running out of time, so let me write it out. Right? Whatever wave is making up this, some portion is moving to the right, some portion is moving to left. So the momentum value is plus minus h over L. And if you're looking at energy level, you would never see it because you're squaring the value of momentum. For kinetic energy, you don't care about the direction, only the speed matters. So here, once you recognize this, you could say, oh, my uncertainty momentum, that is not 0. That is actually uncertainty that's given by, if I'm plotting out momentum, it kind of looks like this. At h over L, I have this sharp peak, and at minus h over L, I have another sharp peak here. Okay? So who knows what the exact uncertainty calculated exactly is? But let's say that this uncertainty is at least h over L, or something on that magnitude. Then you see now it's all consistent. The uncertainty in momentum, that's about h over L, give or take factor of 10. Uncertainty in position is comparable to L, once again, give or take an order of magnitude. And that is approximately equal to or greater than h. Yeah. So this is one concrete example where you can actually see that the uncertainty principle, and it's the approximate version, is consistent with the actual uncertainties you would calculate based on what you know about this. And there are more mathematically sophisticated ways to calculate all this, and I really do want to cover it because it's fun. It only takes a little bit of calculus and not much linear algebra. Let me do that after your exam too.
So this is the simulation that I think helps you visualize the particle represented as a wave packet. So let me download it and run it. So this is the simulation, run it in browser or do like what I did, download it and run it here. Okay, and so this is what I mean. This is the wave mechanical representation of a particle. It has a lot of properties that are similar to particle. I think most important of which is that it's localized. So there's some small region of space where the particle has non-zero significant chance of being found. And way outside of that, the particle has a 0 chance of being found. So when you, for example, make the position measurement, measure the position of the particle here, then that's what make a quantum measurement is. You will see that each time the particle is found somewhere within this envelope. I'll just do this 5 times so that you can see it. So I did it once. Let me reset the system. Particle is prepared in an identical way. I measure its position. Now it's found to be here. That's the second try. Let me just do it 3 more times so that you can see the particle is found somewhere in this range, but always at some random location. Like the particle is right now here, and the next time I measure it, it could be exactly there. It's one of the most likely location for the particle to be.
but it could also be at a slightly different location. Okay, that was my measurement 4. Let me just do one more time. So yeah, so those are kind of position measurement of that particle wave packet. One thing I want to highlight is that, at this position way out here, the particle had more or less 0% chance of being there. I mean, it's not exactly zero, but it's close enough to zero that you could make measurements for the lifetime of universe, and not once it would be here. So, so for all practical purposes, it's zero. So yeah. Now, um, as I pick out, before I pick out one question to do out of this section, one thing I want to highlight is, highlight and maybe explain, is a kind of a discrepancy that you might notice between wave function and probability density. Because for the eagle-eyed among you, you might remember the probability density is the wave function absolute value squared. And note that, hey, isn't the wave function zero here? When you square zero, why isn't it not zero there? So you might see that, notice that, and ask a reasonable question. Hey, why? Where's my node? Here's a node there. What happened to my node? And what you have to understand here is what they're plotting, it's the real part of the wave function. So in quantum mechanics, wave functions have to have complex representation, except unless you're dealing with a bound state. When you have a bound state, then there's a theorem that proves that you can represent it as a real function. But outside of that, wave functions are, especially traveling wave function like this, is represented as complex exponential. So when you visualize it, you have some choices. You could choose to do it as real part only. You could choose to represent real and imaginary part, or you could choose to represent the magnitude. There, okay, now it's beginning to look similar. But if you are looking at only at the magnitude, that's basically square root of this. So you've lost quite a bit of information. So you need to include a phase factor in order to have a full information about wave. And so uh, looking back at my education about quantum mechanics, I think a big chunk of it was just understanding significance of a phase factor when it's not important and when it is important. So I think the visually what makes most intuitive sense usually just real or real and imaginary parts. That I think you can kind of see enough of the wave reflecting here and things coming back. Why is it running so slow? Is it because I'm this feels a lot slower than it ought to be? But anyways, so that's kind of the thing. Okay, let me see what question out of here that's worth doing. I guess I have to. I've done some of this already, kind of informally as I was playing with the thing. Let me try it this way. So I think I'm not really gonna answer any of the questions, but what I will do is, since it's called quantum tunneling and wave packet, let me show you what quantum tunneling is and what it looks like. So at the moment, I'm gonna make the width of the particle broader. That makes the uncertainty of particle wave or particle momentum lower. So it makes the uncertainty in its kinetic energy lower. And that's kind of what you're seeing here. This spread in the green bar, it visually represents the uncertainty in energy. So with my broad packet, this wave has, let me make it broader. Okay. What I want you to do was I want you to set it up in such a way so that the most of this wave packet has greater energy than this barrier. So so you could make a guess. As this wave is incident on the barrier, what would happen? If this had been a classical particle and this had been a classical potential barrier, it would go over it. The particle would slow down as it claims the barrier, and then it would speed back up as it goes down. And like all of it will go through because this potential barrier is not high enough to stop the particle. Now, quantum mechanically, something interesting happens. Watch. So you do see most of the particle get through. Okay, that part is not that surprising. But watch this. There's some part of the particle that's reflecting back. So quantum mechanically, even when the potential barrier is not high enough to actually stop the particle, there is a non-zero probability of the particle bouncing off. In fact, this is you can actually describe the phenomenon of the um, light reflecting off of a transparent boundary. When the light goes from one medium to the other, it has some intensity that's refracted and some intensity that's reflected, and there's a direct analog between that phenomenon of refraction and reflection and this what you see here with this barrier that's not actually high enough to stop any of the classical particles. So that's one. Now, the other way in which this quantum mechanical representation results in a result that it's classically difficult to explain, and this is what we refer to as tunneling. Now, I have changed the parameters here in such a way that the particle does not have enough energy. To a great deal of probability, the particle doesn't have enough energy to make it anywhere within this barrier. So classically, all of the incident particle should be reflected away. Now, when you do the experiment, you do see that quite a bit of the instant wave is reflected. You will see quite a deal of probability amplitude being reflected back to the left. But see here on the right, there's a non-zero probability of particle being here. And if I zoom in on the probability density, oh wait, it doesn't. Well, you can kind of see that this is 1 pixel above 0. So there is non-zero probability of detecting the particle here. Now, as I make the quantum measurement, I would have to make it so many times that I won't bother. But if I were to make the quantum measurement, I don't know, 10,000 times, I think 1 out of the 10,000, it'll be here. Right now, I don't have time to do 10,000 times. I won't, but there is a meaningful non-zero probability of particle being found beyond the barrier where it didn't actually have enough energy to be there. And reading through this in preparation of this meeting, I noticed some things that this exercise demonstrates that I think will hope reinforce the classical intuitions that you have, but recast some of those intuitions in a way that's compatible with wave mechanics. And so, choose the potential to be constant and zero EV. So that is actually valuable in that it can demonstrate some things. So when I do that, as at first sight, it might look like, oh, nothing interesting is happening. I mean, this is spreading out for some reason, but other than that, like, okay, this wave packet or pulse is moving from left to right. What? Okay, I guess that's it. And what's useful here is that this actually demonstrates the uncertainty principle. You might remember from your reading about uncertainty principle. It's the one that says that if you measure two values simultaneously, two values, or for a given wave function state, if you estimate an uncertainty in the position of that wave function, or position of the particle as represented by the wave function, and uncertainty in the momentum as represented by the wave function, then there's a minimum value to that which is h bar over 2. So this combination on the left-hand side, it can be greater than h bar over 2, but it cannot be smaller than h bar over 2. And this simulation at this stage is already already demonstrating this relationship. Now, superficially, it might look like that this wave function, it only shows the only shows the position uncertainty. It shows a bit of a spread of the wave function about 2 nanometers, so that when you make a quantum measurement, you have some probability of detecting it in one place, but you might also detect it in other places. And if you imagine making this measurement, I don't know, 1,000 times, you'll get a kind of a histogram. And that histogram will look like this probability density function. That's kind of the meaning of probability density. So one could ask, how does this illustrate uncertainty in momentum? And there's 2 different ways to get at that uncertainty in momentum. One is the what you might call uncertainty in the wavelength. So when you look at this wave function from here, this is showing the real part. You can also show the imaginary part if you want to make sure there's match from here to here. This shows something that, so it shows you what looks like one wavelength that looks like about a nanometer. But what you have to be careful here is that if you truly had a wave function of wavelength 1 nanometer, this thing would repeat that that pattern you see over 1 nanometer for infinite duration of infinite expanse of space. Unless it does that infinitely, it's not at the fixed wavelength. The kind of the mathematical procedure you have to go through to get a shape that looks like this, get this localized wave function, is you have to combine a wave of wavelength about 1 nanometer with other waves of a shorter wavelength. And what ends up happening is that in this, you can arrange them in such a way so that in this one region, they all constructively interfere, so that you get this little bump, and that's your wave packet. And at these outer edges, they get out of phase and they destructively interfere, so that you get more or less a flat line. And this is mathematically more precisely described and well-defined in terms of the Fourier analysis, which we won't get to today, but it's in part B. So so that's one way to see how there is the uncertainty in momentum, that there's an uncertainty in wavelength, and you can go from the uncertainty in wavelength to the uncertainty in momentum. And that's all the lecture done. Now, there's another way to estimate, measure the uncertainty in momentum, and you can do it as a more direct measurement. And I think that's described in one of these steps here. Let's see. Here it is. I did describe it here. You are going to measure the uncertainty in the momentum of the wave packet, and this is how you do it. This is describing a way to directly measure that uncertainty in momentum. So when you saw me run this simulation, you saw this wave spread out. And I want to tell you that this is spreading out the wave. It's something new. It's not something you have seen before when we were dealing with light. Like you could have a pulse of light, and that pulse of light would not spread out in position as it propagates through space. And there's a reason for that. The second postulate of special relativity, light always travels at speed c. So both the long wavelength light with less amount of energy, less momentum, and short wavelength of light with more energy and more momentum, they both travel at the same speed, c. So they have no reason to spread out. Now here, this wave packet is describing does it say it's an electron? Yeah, electron wave function view. So it's describing an electron which has mass. So which means when you have different amount of momentum, because of its mass, its velocity is not c. In fact, if we are dealing with a non-relativistic electron, we have this relationship between V and P, between speed and momentum. Speed is momentum divided by mass, non-relativistically. So that's what we're seeing here. The portion of the wave that has kind of moved farther ahead, you can kind of think of that as that's the faster velocity or higher momentum component that moved ahead faster than the average of the whole collection of the momenta that made up the wave packet. Or the part that's falling behind, that's the slower part of the wave packet. So the fact that this wave packet spreads over time, that's one, it's directly showing the distribution of velocity. So starting with that uncertainty in velocity, you can infer uncertainty in momentum. And that's what the simulation is showing. And I think when you go through these estimates precisely, you should find that because people who programmed it knew what they're doing. You should find that the way this simulation is programmed, it should show the uncertainty principle holding, as in when you go to the initial condition and when you calculate the product of the uncertainty in position and momentum, they should be greater than or equal to h bar over 2. And this simulation also demonstrates that this relationship is an inequality. It's not an equality, because at this point, there's certain amount of position and momentum uncertainty. And when you look at a later point in time, now at this later point in time, you don't have any more precisely defined momenta. All the wave components that were present at the beginning, they're still here. And so the uncertainty in momentum did not go down, but the uncertainty in position went up. So if this product was right at the limit before, now it'll be greater by like factor of 3. Because the spreading out is spread out by about a factor of 3, even though the uncertainty in momentum does not go down. And there's one other thing you can do here to illustrate how the narrowness of the wave packet is tied to the momentum uncertainty. Here's a kind of a drastic example. So I have this thing paused, and I can make a quantum measurement. I can make a measurement of position. Okay, position is measured here. See how sharp this wave function is, because we're trying to represent within my precision of measurement, within, I don't know, 0.2, 0.3 nanometer, I have localized the particle, I have detected it here. Now, when I let the simulation run, you will see something striking. The wave just spreads out. It's because this highly localized wave function, it wasn't necessarily associated with a high uncertainty in momentum. This uncertainty was in fact large enough that some portion of wave function actually goes backward. Because with this highly localized wave function, the uncertainty in momentum is large enough that this has to include components of wave that's actually traveling to the left instead of to the right. So that's one. And maybe a slightly less dramatic example is you can actually vary the initial width. And I think the simulation always tries to, that's position, not width. This simulation always tries to prepare this wave packet in the minimum uncertainty state. It tries to put together this packet in a way where this product is minimized as much as possible. So when you make the wave packet narrower, then you will find that narrower, but not as narrow as it was when I made the measurement. You will find that this actually spreads out more quickly due to the greater uncertainty in momentum. And if I make the wave packet broader than what it was, so it's starting out broad, but as it travels, you'll find that it doesn't broaden out more as much. Because it has a smaller amount of momentum uncertainty, meaning smaller amount of velocity uncertainty. And sometimes you can ask and answer this interesting question of, okay, what value of sigma would you have to set at the start in order to make the width when this particle reaches here minimum as small as possible? And I think that's actually yeah, I don't ask that question, but if it's something you want to answer, you can. And it's something that I think, reinforces your mechanical intuition that velocity and momentum are related this way. And in quantum mechanics, where we are introducing some strange new things, so we are doing that, but some of the ideas that we learned in mechanics, like this, V is equal to P over M, doesn't simply go away. There are still ways in which to feed our understanding of quantum mechanics, make sure that it's consistent with other things we learned in the classical mechanics. And all of this is, I guess, kind of all subsumed in the correspondence principle, that to the extent that you can take the quantum mechanical things to the regime of classical mechanics, which has been experimentally verified, to the extent that those regimes overlap, what you have verified in classical mechanics should continue to hold in quantum mechanics.
Let me start out with meaning of wave function. And we did talk about this, but we didn't quite do, I guess I mentioned the phrase probability density, but after that we didn't do anything with it. So I was thinking about how to introduce this, and then when I was looking through your book, I realized your book did it exactly I wanted to do it. So because what we are going to now say is this. When we look at wave function psi, as I briefly mentioned before exam 2, that this psi of this wave function, there's no definite physical meaning we can assign to this. We can calculate probability density with this, whatever that means. So the place I want to start out from is kind of a unique example where the wave function actually does have a meaning. Because so for the matter waves that we are going to talk about, what I just said will be correct. Like this doesn't have any physically assignable meaning. So but like just leaving it there doesn't give you any intuition, and doesn't give you any intuition for what we are going to do next. That's why I want to bring up this example, which I discovered as I was looking at that your textbook does bring up. So what I think you should think about is the example of double slit interference of light, where you have light waves coming in and the photons being detected on this screen. I think you saw a version of what they are illustrating here with a simulation some time ago, right? So this is what you see with the high intensity light. When there's enough intensity, then you see this smooth thing. When you reduce the intensity so much that you detect one photon at a time, this is what you're starting with. And as you accumulate more number of particles, eventually this pattern emerges again. That's what you saw with the simulation. Now this is what I want to point out with the example of light wave. So what is waving? What is oscillating in light? Like, this wave front, it represents something. This wave front, it represents something. What does it represent? Like what physical quantity does it represent? Yeah. So electromagnetic wave, which if you describe it in English, is oscillating electric field and magnetic field that's coupled in a particular way. If electric field oscillates up and down, magnetic field oscillates sideways. They're coupled in a way that they propagate in a direction. So what you can say you can actually say what's oscillating here. You can say it is the electric field expressed as a function of position and time. So in this particular example, you could call this the wave function. This is my wave function. But in this special example, the wave function actually has physical meaning. It's the electric field. Right? Now, what you see on the screen, what you see here, does this represent actually the electric field, or does it represent something that's related to the electric field, but not quite the electric field? Like, is there one word that describes what you see on the screen? Intensity. What they are plotting here is intensity. So this is where intensity is 0, and these are the locations where intensity is at maximum. Is the intensity ever negative? Why is it not negative? I know electric field oscillates from positive to negative.
Because it's a square.
It's a square, right? You guys remember from what we did in optics that this, this intensity function, intensity function, it's proportional to the electric field squared. Or if you want to be a little bit pedantic, absolute value of electric field squared. This absolute value is especially useful if you took to this representation of electric field that I was trying to get you to without really, you didn't really need to back then, but you could have used this complex representation of electric field. E naught times e to the I kx minus omega t. For plane waves, if you used this as your representation of electric field, if you simply took the electric field and squared that, if you simply took this and squared that, that wouldn't really do, because what squaring this does is, so you square the amplitude, and for this complex exponential, you just raise to the power of 2. And so you still have complex exponential. You don't want that. You want a time averaged quantity. So the mathematical procedure for doing that is, so this is the wrong answer to get. So the mathematical procedure for doing that is the absolute value squared, or keeping the complex quantity in mind, this is the complex conjugate times the original function. That's what absolute squared means in the context of complex numbers and functions. That was actually your last multiple choice exam question. If you knew that, if you had to remember that, then it came out pretty simple, because this multiplied with its complex conjugate just gives you 1. The I in the exponent cancels out with the minus I in the exponent that you're multiplying with. Okay, so this is where I want you to develop the intuition that the intensity, which describes what you are measuring on the screen, is given by absolute square of the electric field. And we are going to take this model to this matter waves also. So we are going to say, so what's changing with the matter waves is that if you are trying to assign a meaning to this, then there isn't really a meaning. Think of this example here. Example of an infinite square well with a single electron inside it. And somehow the states of this electron are represented with these different wave functions that you have seen before. The ground state wave function, the next excited state wave function, and the one above that, and so on. Somehow the state of this electron is represented with these, but if someone asks you the question, what is doing the oscillating? There's nothing, physically that would correspond to that. Like, what is, there's no collection of particles you can say is whooshing back and forth. It's not like a sound wave like that. It's not electric fields, so there's no meaning you can assign to this. But you can assign a meaning to the absolute value squared of the wave function. And what that is like is it's almost like intensity. But we have to refine this notion a little bit because the reference to this as intensity made sense in the context of double slit interference experiment with photons. It might even make sense if you are doing this experiment with electrons. Then nothing really changes. Like intensity of light is directly proportional to the number of photons you are counting. So you could say intensity of electrons is the number of electrons you would be counting, right? You could say that. But when you now think to this example, referring it to as intensity kind of breaks down, because you are always going to measure one electron. Like, so number of electrons you are counting, that's not exactly right. And this is where I want you to start thinking probabilistically, as in when you look at this plot of intensity, then, so this is where it's going to get more abstract. So this is the kind of plot of intensity, right? Yes? And when you look at this, I don't want you to think about actual photons being detected. Because if you're looking at actual photons being detected, and we are going back to this, counting tens of thousands, millions of photons, and eventually building up an actual pattern. But I want you to think of this as giving you the likelihood of finding a single photon at a particular place. So as an example, what is the likelihood that you would find, I guess I should use a cursor, it's more stationary. All right. What is the likelihood that you would find a single photon, that a single photon would be discovered at a location where the cursor is at? What is the likelihood of that happening? Pretty low, like 0, right? All right, and that applies to all these other dark fringes as well, right? You would never find a photon there, or kind of never. So then let me ask you this question. If you had a single photon going through, what is the likelihood of finding it at this location? Pretty high. Now, would you say 100%? No, why not? Yeah, other points. It could fall here, it could fall here, it could fall anywhere along this vertical line. So now this does represent one of the places where the photon has highest likelihood of falling on it. Now, let me slightly rephrase my question. If you had a single photon go through the double slit, what is the likelihood that it would fall somewhere within this entire pattern? 100%? Yeah. So what we are describing here is what we are going to call probability density. So let me give you a graphical representation of probability density. So this is probability density. I'm going to use capital P as a function of x. And let me just say, this is my x equals 0. All right. So the probability density, it looks like this. And for some reason, it's 0 here. Let me do it in different color. And at some point, it comes up, down, 1, 2, 3, 4, 5. Up, down, up, down, up, down. Wait. And you have a maximum value here. Let me just call it P max. Now, what I can tell you is that this is not going to be equal to 1. Okay? For 1, it's in the wrong units. We'll talk about units in a little bit. What is equal to 1 in this case from our discussion?
The area under
The area under the curve should be equal to 1, right? So if I'm going to just shade that area. So if you have that area and calculate it, so that area should be equal to 1. Now, mathematically, how would you represent that? Yeah, you do it with the integral. So this is your curve, not wave function, just a curve. And you integrate this curve as a function of x. So what you are integrating is this curve with respect to x and over all space. Let me just say all space for now. And what that usually means is from x approaching negative infinity to x approaching plus infinity. Everyone agree that that's the correct integral to do? So this kind of tells you what unit this probability density should be. Everyone here is clear on what unit of 1 is, right? It's unitless. That's why it's 1, no unit. What is the unit of dx? It's length, right? So this says unit of meters or length. So what must the unit of this be so that this comes out right? Yeah, it should be 1 over meter so that the units cancel out. Because in the integration, the important part is this integrand. The rest of the procedure, you're just adding up the terms together. That doesn't do anything to the units. So when you look at the integrand, that tells you, looking at what your variable of integration is, that tells you what this is. So this probability density, it should have unit of meter to the minus 1. So this maximum could be, I don't know, it could be at a value of 0.2 inverse meter. Like that's a possibility. But it wouldn't be at it wouldn't be at 1 meter or 1. It would have this, you need to have this correct unit. Yeah? So that's a probability density. And in fact, so this is what we have been ignoring so far before exam 2, because I didn't want to model, I didn't want you to have to worry about this for exam 2. We are now going to start imposing this requirement. This is called normalization requirement. Normalization meaning that that when you take the probability density, integrate it over all space, in this class we are only going to do one-dimensional example, then that result should give you 1. Yeah? So let me actually give you some examples. I guess we've been talking about infinite square well. So let me give you the examples with the infinite square well so that you have something more concrete to look at beyond just that pictorial representation. So I guess I already have 3 states written out here. Let me just fill in some of the gaps so that I can actually give you actual functional forms of the wave function. Tell you what the probability density should be, and then go from there. So let's see. So these all represent the 0 level for the functions that are drawn here. So this would be my ground state, E1. It would be E1, I'm sorry. So that's the energy E1 for that energy level. This would be described with some wave function. Let me match the colors. Wave function, psi 1. And I'm going to draw the time-independent state. So as a reminder, this is what it means. So this time-independent stationary state, it's sort of what it looks like. It's psi 1 of x is equal to some amplitude times sine of I guess I will explicitly write it out. So let's say this goes from x equals 0 to x equals L. Then the wavelength of this is 2L. So what I write here should be pi x over L. Does this seem right? How do you check if this is right?
The boundary, check the boundary.
You can check the boundary. Like when you plug in x equals 0, it's at 0. When you plug in x equals L, sine of pi is 0, it's at 0. But it's not at 0 after having gone over a full cycle. It's at pi is half of a full cycle, so it's at 0 after having gone over half of a cycle. Yeah? So this is what's called, I guess, let me write it down. It comes with several different names. You could call this time-independent solution. And I actually don't remember what your textbook calls it. So let me just give you all three that I can think of right now. Time-independent solution, or solution to the time-independent Schrodinger equation. You could call this energy eigenstate. Everyone here knows what the phrase eigenstate or eigen refers to? How many here have heard the phrase eigenvector? It comes up in linear algebra. And what it is it's a special solution. It's a special solution like x unit vector is a special vector. Y unit vector is a special vector. Let me just leave it there. Otherwise, it's just a weird mixture of German and English phrase. I'll just leave it there. Next year, Math 3E will be co-requisite to this class, so it'll be better next year. And the third term is the stationary state. They all mean the same thing. So a particular state cannot be a stationary state unless it's also an energy eigenstate. And a particular, well, I guess stationary state and time-independent solution, they seem like they're saying the same thing, right? Like time-independent because it's a stationary. And truth is, this state is not really stationary. It's like a standing wave. When you look at a standing wave, it's not like frozen like this. The wave is oscillating up and down, right? So the same is true of the quantum mechanical, quote-unquote, stationary state, which could be like analogous to standing wave. So to get that time dependence, this is a mathematical relationship that holds for these stationary states. For these states, they have a very simple time dependence. Because it's an energy eigenstate, it has a very particular energy value, let's say E. Then the time dependence of these states can always be written in this form. The time dependence phi as a function of time will be this complex function, e to the I, and then the frequency that's associated with this energy, which is h bar omega. So I'm going to just solve it for omega. So E over h bar times time. This is the time dependence for all energy eigenstates. And so given this stationary state solution, somehow if you know if you find out the energy, you should be able to, once you have the wave function, then you can construct this as the fully time-dependent wave function. The fully time-dependent wave function is the stationary solution multiplied by this time dependence. Once again, for stationary state. I guess I should probably put quote unquote stationary state. Okay? So with this in the background, when we talk about these energy eigenstates, I'm going to fall into the habit of only using the time-independent solution, and soon using almost exclusively time-independent Schrodinger equation. Because we are only going to limit ourselves to talking about energy eigenstates, and that will make the time dependence very simple. Like, does everyone see why I keep calling this simple? It might take a while to see it. So remember, we did all these quantum mechanical waves. Our eventual goal is to calculate this absolute value squared. What happens to this function that's multiplying when you do absolute value squared? Like what this function multiplied to its complex conjugate? 1, right? Yeah, because you are multiplying this with the e to the minus the same thing. So that's the sense in which we mean this is simple. We know when you take this will cancel itself out, and it's that sense in which it is stationary. The probability density doesn't change as a function of time. Okay, so let me write down the remaining other two so that we have some examples to look at as we do some calculations, actually. So E2 will be almost the same function, except with a wavelength that's half as long. Psi 2x, a times sine of 2 pi x over L. And the third state would be similar, psi 3x, some amplitude times the sine of not 3 pi x over L? I guess it is 3 pi x over L. 3 pi x over L. Good? All right. So what I have left uncalculated in the past was I didn't say anything about what this A has to be. I kind of just left it there. It's something oscillating. I don't know what amplitude. Amplitude is meaningless anyway. And in some sense, that is right, because when you calculate momentum or energy, this didn't do anything. Because when you're trying to calculate momentum, what you do is when you're trying to calculate energy of this, what you do is you apply the energy operator, right? So if you want to, so for example, I will do that later, so I won't get too deep into it. So far we've treated this A as a physically meaningless quantity. And so far that's been okay. But now that we are giving definite meaning to this, psi absolute value squared, I guess not as intensity, but as px, or probability density, now we have to be careful what value A will be. So I guess here's one way of making everything sound okay. We can simply say these are, I don't know, unnormalized wave function. And now if we want to do any calculation, anything or whatever, then now we have to normalize it. If we want to do any serious calculation, which is what we'll get to when we talk about expectation value soonish. So let me show you a normalization calculation example. It's actually pretty simple for these. There are wave functions where it's not simple. We won't do those in this class. You'll do them in upper division physics if you take upper division quantum mechanics, which is fun. So let me show you a normalization example. So I guess let me call it this way. So normalization of wave function. Actually, I think I'm beginning to see a pattern here. So let me just do it for general psi sub n, some nth wave function. Because I think what I see is this thing multiplied by n here. That's my general wave function, right? So, so when you are normalizing the wave function, this is the requirement you impose on the wave function. You impose that this wave function, absolute value squared, integrated with respect to x from technically to over all space, but what is the value of wave function below x equal to 0? In this example, what's the value of wave function here? 0, right? It's an infinite square. Well, the wave doesn't penetrate beyond that. And same thing on this end, right? So what all space is, it's going to reduce down to from x equals 0 to L. Because outside of the range, wave function is 0 anyway. And the requirement, so that's a calculation you are doing. The requirement you are imposing is that this must equal to 1. That's the normalization requirement. That's what we said out here, normalization requirement. It's not a difficult calculation, so let's go through. So let's go through. So let me plug in what the psi of n is. It's this. So it's a times sine of n pi x over L. The absolute value squared thing. So sine, this is a real function. So absolute value doesn't do anything. It can be just squared. A, let me keep absolute value thing with a. That was also kind of snuck into your multiple choice answer, which was not all that clearly explained, but wasn't wrong. So I'm still integrating this with respect to x from x equals 0 to L. And that's still equal to 1. Let me factor out what I can factor out. This a here, it's not a function of x, right? It's just an amplitude, a constant. That means I can factor out this absolute a squared. That doesn't need to live inside the integral, right? So what, and since I moved this here, let me, do I want to move it over? Let's leave it here. I don't want to move too many things in place. So what it looks like is what I have to do is I have to do this calculation. Anybody here know how to do an integral of sine squared x? I'll do this quickly. If you want, you can do this on O from alpha. And if you have the pro feature, you can look at the step-by-step function. That'll help you, I don't know, remind you what you should know. So this is the trig identity I'm going to use. The trig identity is that sine squared theta is equal to 1 minus cosine of 2 theta. I think that's right, over 2. Is that right? Let me just quickly derive it because it's easier to start out with something I'm sure about. So what I am sure about, cosine of 2 theta is equal to cosine squared theta minus a sine squared theta. And what I can do here is I can rewrite one of these two things in terms of the other. Let me rewrite cosine squared theta. So cosine squared theta is 1 minus sine squared theta. Right? I still have minus sine squared theta. So I have 1 minus 2 sine squared theta. Good? Everyone agree that's cosine 2 theta? So sine squared theta. So move this over, is equal to 1 minus cosine of 2 theta divided by 2 over 2. So I guess I did remember it correctly. I don't know why going backward it didn't work. Yeah. But that's the trig identity you're supposed to have memorized. So this is what I'm going to use to help me do this integral. This is called the power reducing formula. It helps you reduce this power so that you have something that's just linear in the trig function that everyone here should know how to integrate. So let me just copy this over here. Sine squared theta is equal to 1 minus cosine to theta over 2. And in the end, I'm actually doing more work than I need to do here, because something's going to go to 0, and the overall result will be actually fairly simple. But I'm just doing everything to make sure, because this is now supposed to be rigorous quantum mechanics. So I want to minimize what I skipped. So what this becomes is I still have absolute value of a squared, and still the same integral from x equals 0 to L, but this is now rewritten into this form. So I have 1/2 minus cosine of 2 times all of that, 2 n pi x over L over 2. Integral with respect to dx is equal to what? Everyone good? So this is where I kind of want to take a shortcut. Or not shortcut, I want to just argue my way through and not really write anything down. Focus on this one term here. Cosine of 2n pi x over L. When you integrate from x equals 0 to L, you are integrating from the argument to cosine from 0 to 2n pi. So it's an integer multiple of one full cycle, right? When you integrate cosine over integer multiples of a cycle, what do you get? 0? Yes? Yeah, so this whole thing is going to turn out to be 0 when you finish the integral. So instead of going through all that trouble, we say, all right, it's 0. We don't have to do anything with it anymore. All right. So then this whole integral becomes very simple then. Just 1/2 integrate from 0 to L. So this whole integral is just L over 2. So this finally gives us the constraining equation for normalization. We get this, that absolute A squared is equal to, I'm going to move this over here, 2 over L. So technically what that means is you have actually a range of possible possibilities. So let me give you a form for A that includes all those possibilities. A can be this. A can be square root of 2 over L, that needs to be there. And then it can be complex. It can be this times e to the I phi. Like if you took this, applied it here, would you get this equality? Right? So there's an infinitely many number of A that can work depending on this phase factor. And obviously this is unnecessarily complicated. This phase factor doesn't add any physical meaning. So the convention that people take in quantum mechanics is for these stationary states. In fact, there's a theorem that proves this. For this bound state, you can always choose your coefficient in such a way that your wave function is real. So we are going to follow the convention and just choose phi equal to 0, or this whole thing equal to 1. Or what most of you would have guessed after seeing this in the first place. We are going to go with this. Yeah? But I just want you to know that the other possibilities are there. You can change the phase a little bit. And when you form superposition of different states, sometimes that matters. The relative phase does matter. So this is an example of normalization. It took a little bit longer because I was talking, but this is a fairly simple calculation. So what this means is now when we go back to these wave functions, really to have a wave function that you can use to do useful calculations with, this really should be square root of 2 over L in front of every one of these here. And I guess in this particular case, the the normalization factor didn't depend on the quantum number. The normalization factor here, it didn't depend on n. But I would tell you now that in general case, that's not true. Generally, it could depend on n. It is but here, in this simplest possible case, it happens not to depend on n. So, I guess not have it depend on n.